We brought the bike generator into the lab today so that we can demonstrate alternator ripple current and show you how to fix it.
So I'm going to show you what ripple current is, we're going to look at it on the oscilloscope, and then we're going to show how to mitigate it with some capacitors and a basic equation.
So I'm going to generate some power and Eve's going to talk you through the science.
Alternators are commonly used on bike generators because they're easy to set up and they also have built-in voltage regulation and rectification. The rectifier converts the AC current to DC current. However, these aren't usually that sophisticated because they're connected in conjunction with a lead-acid battery, which mitigates any ripple current effects. So if you have the same setup on the bike generator with the battery, then you won't have any issues. However, if the battery is removed, then the ripple current will not be mitigated and this can then damage delicate electronics. So let me show you what ripple current is and then we'll have a look at it on the scope. The alternator generates AC current, so the voltage over time will look like this. Then the rectifier converts all of the negative voltage into positive, so the voltage over time will look like this. However, you can see that the amplitude of the voltage still varies significantly. This is the ripple current and can be really damaging to electronics. So we're now going to show you this on the oscilloscope connected to the bike generator.
Right, so it's time to get the bike generator going. I'm going to start pedalling to get the alternator spinning up to speed, then I'm going to press the ignition and we'll start generating some power.
So down here we've connected the alternator directly up to the oscilloscope, so you can see the ripple current traced on the scope. So what I'm going to do now is I'm going to add capacitors in parallel to the load, and what you should see is that the ripple current is reduced. As you can see, if I remove the capacitors, the ripple current is increased again, and when I attach them back into the circuit, it's reduced. As you can see, with the addition of the capacitors, the output goes from the rectified voltage to a voltage with a much lower variance in its amplitude. This is because when the voltage is at its maximum, the capacitors are being charged. When the voltage is reduced, the capacitors will discharge, and this means that the load can still pull all the current that it requires. This effect is increased for using a larger capacitance, however, achieving a perfectly stable voltage is physically unreasonable. The minimum capacitance that you'll need for your circuit can be given by this equation. The capacitance, given in farads, is then dependent on Imax, which is the maximum current that your load will draw, Vmax, which is the maximum ripple voltage that you want, and F, which is the rotational frequency of your alternator. This can be found using this second equation. P is the number of poles on the alternator, usually found on the datasheet, and V is the rotational speed that you'll be running it at in RPM. We found that for our bike generator, if we had a load that was drawing 10 amps and we wanted a maximum ripple voltage of 1 volt, then we would need a capacitance of around 13 millifarads. Because this is a minimum, we've gone slightly above that on the circuit that we showed you earlier. We hope you found this useful, and if you have your own bike generator you're working on, or if you just have any questions, do let us know.
If you want to find out more about our bike generator, check out the playlist, including us trying to avoid kettle using it.
We do also have lots of interesting science videos from here in the lab.
Thanks for watching.